I was recording and it stopped recording. We're gonna do the with. I've already done it, so we're not gonna do it. I'm gonna walk through the daily integral. Uh, one of the day. It's not the daily integral today. It's previous daily integral now. E to the I. I'm just writing it back out. I'm very underprepared. My notes on this are terrible. I just have the math. I've got massive jumps in my work that are gonna be hard to explain, and we're just gonna go for it. We're just gonna. I'll make. I'll explain. So this looks horrible, right? The integral between minus pi over 2 and pi over 2 of the sum running from cosine from n equals 0 to infinity of cosine of pi n over 2 over gamma of n plus 1 times the real part of the imaginary part of e to the ix over the real part of e to the ix, all to some power n. Wow. I saw this. I put on my Snapchat story. I give up, never doing daily integral again. And at first glance, this looks horrifying. We've got a gamma function, an infinite series. We've got real and imaginary parts, and a tangent hiding inside everything. But the whole strategy is to slowly strip away the complicated notation until the integral reveals a familiar Taylor series. Okay? So, let's just start off with this whole real imaginary chunk, because that's probably the simplest part of this whole integral. And it doesn't look it, but it is. So, what is e to the ix? Let's zoom in. E to the ix, we all know, is I sine of x plus cosine of x. Now, the imaginary part of this, I'm going to call it z for now. For now, don't. Whenever I write something, don't think of it as now when I next say z, we're still talking about this. I am terrible with notation. My work is so sloppy. Just we're calling this z so I don't have to rewrite out e to the ix. The imaginary part is going to be the sine term, sine of x, and the real part is the cosine term. And we have the imaginary part over the real part, so just sine over cos, which is tan. So this just is tan to the n, the real part of tan to the n of x. Yes, yes, dx. We can forget about the dx for now. And this is confusing. This confused me because what is the real part of tan? It's all real, right? So it is just a decorative thing, I think. I'm not too sure. But this is just tan n to the x. Okay? So we simplified our complex expression to tan n to the x. So let's rewrite out the integral now. It's going to be a lot of rewriting integrals. I equals integral between minus pi over 2, pi over 2. The sum from n equals 0 to infinity of cos pi n over 2. Bang, bang, all over. What was it? Gamma of n plus 1. How could I forget? Times tan n of x dx. We've done that. So now what happens? Whoa. This again something I didn't really explain in my notes. The key observation is parity. So the odd powers of a tangent are odd functions, and even powers are even functions. So for tan n to the x, right? See, I'm not very good at explaining this. Minus tan if n is odd, and then tan of minus x if even. That. So tan of minus x, like this, is going to be minus tan of x. So basically, tan to the n of minus x is minus 1 to the n of tan to the n of x. So odd n gives an odd integrand, and even n gives an even integrand. So if we combine that with the cosine coefficient that we have, which is cos of n pi over 2. It's going to be 0 and then minus 1 to the k, and odd n equals 2k. And this is very important because it explains why the odd terms kind of disappear. So we're going to replace n with 2k. And so it becomes two lots of the integral from 0 to pi over 2 of the sum running from k equals 0 to infinity of minus 1 to the k. I'm just checking if this is what my notes did. I have wrote f of x equals minus f of minus x. So f of x equals f of minus x, as we just said. And then the integral between minus a and b of the function equals two lots of the integral between 0 and a of the function. Okay, sure. We'll rock with it. Gamma of 2k plus 1 now. Tan to the 2k. X. The x. Sorry that there's no brackets. So now n is even, right? It's the 2k. So cos of pi n, did I just write this? I swear I just wrote this out. Equals minus 1 to the n. I did. Okay. I should probably read my notes as I talk. And then gamma of 2n plus 1 now is just going to be the 2n term factorial. So we are now left with. I've got two lots of notes. I've done this twice. So as I'm reading over one part and then looking at the other and checking if I've got the same thing. So I'm going to write out this. I think I've done this step. I equals the integral between 0 and pi over 2 of minus 1 to the. No. Yes. Minus 1 to the n tan 2n of x. I know I'm jumping between k and n. Like, just so someone doesn't fucking annoy me. Of gamma 2n plus 1. I will use these terms interchangeably. No, we don't need the gamma. We've just spoke about this. 2 factorial, sum, 0 infinity, just pretend there's a there thing. Hope you're happy. Dx. Cool. Now, have a look at this. Minus 1 to the n, tan to the 2n of x over 2n factorial. Does this look familiar? Does it look familiar? There is a Taylor series, the cosine series. Okay, what is that defined as? Well, cos of x equals the sum from n equals 0 to infinity of minus 1 to the n. I didn't even write this bit down. X to the 2n, I think. X to the 2n over 2n factorial. Yes, it is. Because I wrote x equals tan x. So this makes sense. So look, they're very similar. All we're out by is this factor of tan. So we're going to say that let x equal tan x. Um, so this is going to be cosine of tan x. So that's our sum that we have up here, right? This is this. So what we're left with is just cosine of tan x. So we now have the integral between 0 and pi over 2, right? Haven't done anything with the limits yet. We have two lots of this integral of cos of tan x dx. Nice. Nice. It's working. Um, this took some time um to like think of, and yeah, we're here now. And in a minute, it's gonna really get sloppy because it evaluates down to something that I did not too long ago, and I recognized it, and then I was like, "Oh, just roll with it." But from here, this is some simple, you know, we can say u equals tan x, du equals sec squared x dx. So sec squared x is 1 plus tan squared x. Hang on. I've got very ahead of myself because in my notes I wrote alpha. 1 plus tan squared of alpha. I wonder if anyone can guess what we're going to do next. Okay, that's fine. Dx equals du over 1 plus u squared. Anyone starting to guess? Anyone starting to notice? What does the lower bound become? This is going to stay 0, but the upper bound is going to go to infinity. So we now have, I wrote finally in my notes, I equals, um, the two go. The two disappeared. I'm just gonna go with what my notes say. No, it should. There should still be a two here. I'm just making. No, I'm not. The two goes away somewhere. Otherwise, that would give us two pi over e. Two e over pi. The two's gone. Forget about the two. Wow, what a mathematician. I sound like an engineer right now instead. Um, of 0 to pi over 2, cosine, no, cosine of u all over 1 plus u squared. This shouldn't say pi over 2. We just changed the bounds. Literally just changed them. Du. Do you recognize this? I did. We are going to have to define um, parameter here. That's why I was talking about I wrote a 1 plus tan squared of alpha instead of x. Um, so now we can define a parameter. So we're going to say I of alpha as a function of alpha is going to be this integral between 0 and infinity of cosine of, whoa, alpha u of 1 plus u squared du. Cool, right? So then our original integral is I is 2I of 1. It doesn't matter. Just forget about the 2. I've already said forget about the 2. It's staying in my head. We're now going to differentiate under the integral sign. I haven't really wrote it out. I've just kind of done it. So I prime of alpha is gonna be minus the integral from 0 to infinity of u sine alpha u. I'm also using t and alpha interchangeably in my notes, of 1 plus u squared. Usually I do I as like I of t, but I'm using alpha. So there's some annoyances in notation. Someone, a real mathematician, someone at university reading this would be screaming at me. Um, it doesn't really matter. I double prime of alpha. I wrote t. What's funny though is I wrote t like in here, and then I wrote alpha in here. Yeah. But u squared cos of alpha u. I'm sticking with alpha over u squared plus 1 du. So now we can look at the algebra of u squared over 1 plus u squared. So u squared over 1 plus u squared is the same as 1 minus 1 over 1 minus plus u squared. Okay. Is that what I wrote in my notes? I'm getting ahead of my notes now. I wrote, yeah, the exact same thing. Cool. Now what does it become? I double prime alpha is going to be minus the integral from 0 to infinity of cos of alpha u minus cos of alpha u all over 1 plus u squared u. Cool. Cool, 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 cool. Um, should that not be minus the integral? Should it not be minus the integral of cos alpha u plus the integral from 0 to infinity of cos of alpha u over 1 plus u squared? I just took them away. Hmm. Um, I think it should be. I think that's a mistake in my notes. I think it should say this. Because now the second integral is exactly the original integral. You agree? See? It's the same. So really, yeah, I think this was a mistake I've made. Yeah. Okay, it's fine. I prime of alpha, double prime of alpha is just gonna be minus the integral from 0 to infinity. In fact, I don't have this in my notes anymore. Now I'm in like fucking looking at epsilon, so now I'm gonna have to do this live. Cos alpha u plus that. Okay. So the integral cos alpha u doesn't converge ordinarily. You've got to regularize it. Yes. So it's now we introduce um to do that. Oh, this is the worst explanation on YouTube. So we're gonna say um the limit of epsilon going to 0 of bang 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 e minus epsilon u e to the I alpha u du. Right? So it's a standard damping trick to make oscillatory integrals behave. Um, so this term becomes 1 over um, e to the minus I alpha, I think. Oh, wait, let me just give me a minute. I'm gonna have a minute where I just don't speak and just, yeah. Is it minus? Yeah, like that. Of you, du. Epsilon squared plus alpha squared. Um, yes. Epsilon minus I alpha, which is what I was talking about just a minute ago. Um, so that then da, 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 epsilon plus I alpha over epsilon squared alpha squared. we've got here, because we're taking the real part. And as epsilon goes to zero, this tends to zero. So effectively, this integral between zero and infinity of cos of alpha u goes to zero. In the regularized sense, is what we were saying. So now, if we're looking at oh, second derivative, bang, 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 bang. What was it before? Was it minus? I think it's positive. 0 to infinity cos alpha u over u squared plus 1 du. We can say this because it's just the same as the this. Like we talked about it here. We just had to evaluate this time. That's what we've been doing. It's what I didn't do. I just jumped from here to here, and I was like, cool, cool, it's the same, and didn't actually talk about that. That's how. Okay. So now, God, we can form an ODE basically. Because I double prime. So what we can say is bang, 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 bang equals zero. Solving the ODE. So we introduce our characteristic equation. Lambda squared minus 1 equals 0. So lambda equals plus or minus 1. So we can say I of alpha equals AE to the alpha plus BE to minus alpha. Did I use alpha or t? I used alpha. Sure. So now use the k as t goes to infinity. Because the integral is bounded by 1 over 1 plus u squared, we know that I it goes 0, so a is 0, is what we're saying. Um I should probably write out the things I say. That's probably a good idea. So as alpha goes to infinity, um 0, so a is 0. Cool. So now we're just left with the. Oh god, I can. No, that should be an alpha equals b e to the minus t. So, we gotta determine the constant. So we're gonna set t to 0. Did I actually do any of that? No. Okay. So this is gonna be the integral between 0 and infinity of 1 over 1 plus u squared du, which is arctan of u, and between 0 and infinity. And when arctan is strictly greater than 0, it is pi over 2, right? I think the proper, like if you have arctan of x plus arctan of 1 over x, you have just pi over 2. Okay, we'll roll with it. So b is just pi over 2. So therefore, I alpha, not t, is just gonna be pi over 2 e to the minus alpha. And at alpha equals 1, we have 1 pi e over 2. And so, because the 2 from before, um, well, we can say I equals 2 1. So we are going to be left with pi over e, or pi e to the minus 1. Okay. I think this was the mistake. This shouldn't be pi e over 2. This should be pi over 2e. Yes. Yes. Otherwise, it wouldn't work. Okay, cool. So, whew, after all, the gamma functions and the complex notation and the entire problem collapses into this like Fourier type integral, and it evaluates to pi over 2e, giving the final answer pi over e. And yeah, honestly, it's a nice, elegant problem. It was generously submitted by. Let me have a look and see if I can pronounce the name. Haru Masaki. I haven't checked how they solved it. I assume probably the same way. I don't know how else you'd go about doing this. Um, so yeah, I will look at the solution. I know I got it right. I know that the solution is pi over e. But it'll be interesting to see if there was another way to do this. Sorry about my terrible notation, my poor explanations, and having to work things out mid-video instead of having it nicely prepared. But that's maths all over, right? So, hope you enjoyed, and subscribe if you want to be better at maths than Dexter.